Right. I am alive. I exist. I'm here. I'm here. Nobody else is, but I am. I'm here. Da, 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 da. Who just joined with the name of copy? I got two guesses. I could flip a coin. That's probably not what I should do with people's education, but I could. Shoot me a message if you can. Okay. So for today, we're going to do as much math as we can cram into 2.5 hours. This one's going to be kind of messy. We're not going to have any review over the previous classes. Next week, as you know, I have every intention of going over one of the practice exams and explaining everything as I go. Several of you are going to be popping out of my class in the meantime and doing a post-assessment. That'll be happening on Tuesday. I've yet to get the information on whether or not it's up to me on whether or not you pop up for that one. But I know that at least during this class, the people who are currently logged in, who will be on there is Maribel, Sandra, and Geraldine. You three are going to be having a post-assessment next Tuesday. So try to be here. After you finish the post-assessment, you'll just pop in and watch me finish the rest of the problems. All right. So any questions or anything before we get started?
Yeah, we going the same time, 6 or?
Yeah, on the email I got about that, it just says 6:15 is when that's supposed to start. So just try to be here, and then as they're getting things ready, they'll just pull you out.
Okay, thank you.
Okay. So today's going to be a fun one because we're going to be doing equations, inequalities, graphing lines, all the fun stuff, all the stuff you think about when you think of, oh my God, it's math. That's today. So we're going to start off with linear equations. So linear equations usually have either one or two variables. They effectively represent a straight line. Usually, see a message there. But essentially, yeah, it's only, oh, okay. Yeah, it's only going to be a few people. I did not realize that was Veronica. Yeah, you'll be doing that too. It's literally Maribel, Ricardo, Veronica, Sandra, and Geraldine. Everybody else is just going to be hanging out and watching me do math problems. And they're going to be weirder math problems than anything else we've done so far. So it'll be fun. Let me just make a note of the attendance. Yeah, save for a few people. We've actually kept pretty good attendance the whole time. It's like the best attending group I've had. And yes, the post-assessment is effectively an exam. It's going to be like you probably did a pre-assessment when you came in here and started, working towards this stuff. As far as I know, it's going to be about the same test. So it's effectively you get tested before you take the class. You take the class and then you get tested after you take the class, and then they see if you've improved. So it's pretty much just a let's see where you're at test. So it's not going to be a very stressful one. So you should be fine. Especially after this particular class, it'll be fun. So linear equations are the easy type of equations. We've actually done a bunch of them already. It's literally just anything that has a single variable. As you get further in linear equations, okay, I hate this definition of linear equations because to me, a linear equation has two variables. So essentially, when there are things that are two variables, you have an x relating to a y. So depending on what is hanging out inside of the x, that would change what the y is. If you get a bunch of those and put them on a graph, they make a straight line. So that's why they're called linear. But until we move on past that, we're going to be largely just doing things that have, one or two steps. Now, granted, I have done quite a few of these so far during the class. You can see that example at the bottom, x plus 3 equals 5. That's a linear equation. So if you've seen me work those, we've already done a bit of them, so you probably have a decent feel for them. So the thing with linear equations is a lot of people can reason through them. They're very easy to reason through. And I get this from people when they're learning this stuff all the time. Why would you expect me to do it this way when I can do it in my head quicker? And the reason that we're going to do things a certain way at this level is because that method will scale up. Oops. Sorry, I just kind of leaned over and hit the right click when I was turning off the projector because nobody else is here. So why waste the electricity and have that weird hum in the background? So when it comes to solving linear equations, you do them a certain way where you write out what you have, you write out a line where it's everything that's happening to that line, so your operation, and then you write out what you have left. Hi.
Hello.
I got them. Not bad. As you can tell, I got people online.
Cool. We're having some difficulty with the visualizer next door. Might you be able to assist really quickly?
Well, I feel like everybody's okay with me not doing linear equations for a moment. So be right back. Helping the other class. Sorry, guys, I'll be right back. Okay, I'm alive. Sorry about that. I have no idea what the problem was. I could not help. I accidentally turned off their computer and cut off all their Zoom students. So, that's entirely on me. I have no idea what I'm doing. It's great. Future reference, if you ever don't know what you're doing with electronics, just unplug it and plug it back in. 90% of the time, that'll solve your problem. That computer's booting, so we'll see if that solved the problem. Okay, so back to what I was saying. The best way to do linear equations is to write out what you got, like so, then do a line right underneath it where you have that happening. So you do your operation. So since we have x plus 3, in order to get the x alone, we would be subtracting that plus 3 away. So you subtract 3 from both sides because you think of that equal sign as being like a little balance. So you subtract that from both sides. You end up with just x on one side, and then 5 minus 3 is 2 on the other side. So yes, you could very well look at that type of problem, say, something plus 3 is 5, and reason your way back to the something being a 2. But as these problems get more difficult, you want to do it this way because this will make your life easier. So get the structure down now. So when the math scales up, you still have a good way of doing it. Now, one thing I do want to say Kind of a weird way to do it. Yeah, let's see if that's a good idea. I do want to say that sometimes when you look at a math book, some of you might have a math book or some worksheets that you can work from. Sometimes, oftentimes, that second line there where it's just the -3, they'll literally write that as if you have something like this, where they actually leave everything alone and do it on both sides, but they do it all in one line. And the reason I wanted to point this out is because, one, if you go and look at examples online anywhere else, you might see them written this way. So if you see something like that, just think, okay, that means this is happening. Now, why am I pointing this out? Because you might run into it and you're not going to see it from me, because I personally think that is an awful way of writing down what you're doing. It is not very convenient. It's hard to look at. It's hard to wrap your head around what's happening. It's much easier to just have another line where you're just doing whatever to it. And then you can kind of think as the left side being its own deal and the right side being its own deal. Much easier to do it that way. So solving any linear equations work pretty much like that. Every single time you do one of these problems, you're undoing whatever's happening to the x to get the x alone. So if you would look at a problem where it says, oh, x divided by 4 equals 3, how would I solve that? Well, the x is being divided by 4, so we do the opposite. Instead of dividing by 4, we're going to multiply both sides by 4. In doing that, it would cancel out that divided by 4 thing, and you would be good. So one thing I did want to mention is that we are now at the what you do to one side, you do to the other stage of algebra. So that means that that equal sign just means that both sides are equal. So if you change one side and you don't change the other side, you can kind of think of it as being like a balance, like a scale. Suddenly, if you put something on one side, added to one side, as opposed to adding it to both sides, you're going to upset the balance of the scale, right? That's exactly why we have to do the same thing on both sides of an equation. They're equal to each other, so we can't upset that balance. Okay, so here's a couple of examples. And a random meme. Let me write down a few of these guys. They're going to be pretty quick. And one thing I do want to point out is if you look at number 4 and number 5, the way I have parentheses is telling you how I have those set up. So I actually have those set up as fractions. On number 4, you can read that as the 2x being on top of the 5. And then on number 5, you can see that there is a fraction, the 1 divided by 5, and that is being multiplied onto a y. So that 1/5 is actually kind of on its own. Okay, so these guys are going to be pretty quick. These are all just the single step examples. The next sheet is multi-step examples. So for the single step examples, we start off with 2 plus x equals 6. Okay, well, I wanted to put this one up here to show you guys that This is effectively the same as x plus 2, right? 2 and x and 2, it's the same thing. So you can look at that 2 as being positive, right? It doesn't have a negative on it. So if I had to get rid of that 2 to get that x alone, since this is a positive 2, I'm actually going to subtract the 2 from both sides. Just think of it as, hey, there's a 2 there, so what would I do? I would have to subtract it. Now, what do I have left on the left? Well, I just have that x. We don't need to put the plus because that doesn't have anything adding to it anymore, and that plus just kind of showed that that x is positive. So we have x is equal to 6 minus 2, 4. Cool, that's it. That's all we got to do. They're not bad. Same with number 2. You look at that, we have a 2x is equal to 30. Okay, no problem. If that 2 is multiplied onto the x, then we do the opposite to it, right? To get that x alone, we're going to divide by 2. So we do that to both sides. We have an x left on the left. On the right, we have 30 divided by 2, which is 15. Okay. Same sort of things happening on number 3. On number 3, we have x over 6 is equal to 4. So right now, this x is being divided by 6. So in order to undo that division, to get rid of that, we would actually multiply both sides by 6. I just kind of write it that way, kind of like it's kind of floating off into space and being multiplied on there. Now, over here, it's a lot easier to look at, right? 4 times 6, we can do that no problem. That's a 24. But over here, it might be a little weird looking. So what's happening here is you can kind of think of this as being over a 1. If I multiplied those things together, I'd have 6x over 6. The 6's would cancel. So whenever I'm multiplying something effectively onto the top over here, that's canceling the bottom out. So now that we have that in our heads, we can do that every time. You have x divided by 6, you multiply by 6, the thing on the bottom goes away. Now, I made the last 2 to be kind of tricky, because you can do these, well, at least number 4, you can do it as 2 separate problems. You can do this as 2 separate, 2 separate steps, I should say. We can look at what's happening with that x. What's happening to it immediately? Well, it has a 2 being multiplied onto it, right? And then what's happening to it after that? Well, once it's multiplied by 2, it's being divided by 5. Okay, so that's 2 things happening to it. But another way to look at this, another way to look at that is that it's 2/5 of the x. Because, and this is going to be like a little aside example thing, 2x over 5 is the same as 2/5 x. Those are equal to each other, perfectly equal to each other. Since that x is on top, that could come out front. Same sort of thing happens with this 6. Since I'm multiplying by just a 6 on its own, that 6 can also be on the top. So what we can actually do, because we can look at this as a fraction happening to that x, is we can go back to some of the fraction stuff we did earlier, and we could think of undoing a fraction. So if we were undoing a fraction, would I want to divide this side by 2/5? No, that sounds horrible, right? I don't want to divide by a fraction. Nobody wants to divide by a fraction, right? But if you remember, how did we divide by fractions? We avoided the subject. We kind of made it multiplication, right? You flip it upside down, you multiply. Well, that's exactly the concept that you can apply here. We can multiply both sides by that fraction upside down. Now what's going to happen? The 2's are going to cancel, the 5's are going to cancel. What do we have left? Just an x. And then over here, well, we can do it a couple of different ways. We can multiply the 8 by the 5 and get 40. And then it'd be divided by 2 and we'd get 20. Or remember back when we were doing fractions and I showed you guys, it's easier to cancel fractions out before you multiply than after, because I can reduce this 2 and this 8. The 2 goes into itself once, the 2 goes into 8 4 times. And we end up with 4 times 5 on top, and then 1 times 1 on the bottom, so we don't need to show that. We just get a 20. So that might be a bit of a mess. So I'm going to show you guys that one more time, just to kind of stick it, right? We have effectively a fraction multiplied onto the x. So you see something like that, you're going to multiply by the same as that fraction upside down. That's called the reciprocal. So that's the reciprocal of 2/5, 5/2. The fractions cancel out. We have x left on the left. And then however you do this math is going to end up being a 20. So that's all you have to do on these types of problems. Zoom this out a little bit so I can work this next one while you guys see the previous one. So this one, almost the same thing happening, right? We have 1/5 y is equal to 6/35. Okay, all right. So how do we get rid of that? Same sort of thing, right? We don't want to divide by a fraction. We can flip and multiply. Oh, but if I flip this upside down and multiply it, what's 1/5 upside down? 5/1. So this actually works out exactly like this problem up here. This problem up here had x/6. That was exactly the same as 1/6 x. So we have that same concept kind of coming back. That same concept can apply. So this 1/5 y, this is off to my side in my notes, that's exactly the same as y/5. Does that matter too much at this moment? No, it's not going to change what we do for that step. However, that concept is going to come in handy on harder problems. So I really want to drive that home. So what do we do with this problem? We want to get rid of that 1/5. We're going to multiply both sides by 5. Now I have y is equal to, and I'm going to do this as 2 separate steps, just so you guys can see exactly what's happening here. I'm going to rewrite the right side for now. Okay, so we know y is equal to whatever the heck this guy ends up being. But I wanted to show you that you can reduce the same way on this one. This 5 goes into itself once. It goes into 35 7 times. So that reduces to 6/7. Okay. So any questions on these before we do the ones that are slightly harder? Pausing for dramatic effect. No? Okay. Okay, so the next section is just the same concept, but multiple steps. So when I look at these problems, these are the ones where you have to do more than one step to them. And we've seen a little bit of those so far. So we're going to kind of do a bunch of those now to kind of solidify that. So as we move forward in math, equations are going to get more and more complicated. So you can't always be happy to just do one thing and say, yay, it's a problem. You have to be accepting of the fact that sometimes your math problems are going to be complicated, and all you really got to worry about is what is your goal and what can you do to this problem right now. So when we look at these problems, we think, okay, our goal is to get X alone, right? So what can we do about it? Well, if we look at that 2x plus 3 on the left, we think, okay, what's happening to the X right away? Well, it has a 2 on it, right? So it's being multiplied by 2. We could divide by 2, but we can't yet. The reason we can't do that yet is because of that plus 3 off to the side. That 2x plus 3 is causing us a bit of a problem, right? So if we got rid of the 3 first, then we could end up with something 2x equals, and we could divide by the 2. So you have to plan out your steps like that. So if you're on a test, you're feeling frazzled, you're like, oh God, what do I do? This is a big problem. Oh God, what do I do? Just do one step. That's all you got to do. Every time you do something, you do one step. That's it. I am not big on skipping steps. I'm not big on, I combine steps every once in a while when they're easy enough that I can see where things are going to go together. But I don't skip steps for a reason. I always make mistakes if I do that. Gee, I wonder if these slides are from a few months ago. Can you tell? All right. So our first problem is actually that example. Let me write out a few of these first. Okay. All right. So our first one is that example. We can't do anything about this 2 first. Okay. You can, but you would hate yourself if you did it. In order to solve this problem by doing the 2 first, don't write this down if you're taking notes. You would have to divide everything by 2. You can see what kind of mess that's going to make, right? We don't want to do that. We don't want to start giving ourselves funky looking fractions. We want to keep it as simple as we can. That's why when it comes to what do you do first, you think, okay, what's the first thing I can cleanly move away from that X? Well, that 3, right? I can't mess with that 2 yet. We saw how much of a mess that would make, but we can get rid of that 3. So we subtract 3 from both sides. Again, we're writing that as its own line, its own step. Then we write what we have left. 2x equals 7 minus 3, 4. Okay, now we got 2x is equal to 4. That's great. Now we can divide both sides by 2. And it works out very nicely, right? So technically, you could divide each and everything by 2 to start, but then you'd be playing with 3 halves and 7 halves. And you probably are avoiding fractions as much as you can. And honestly, even if you're not, this is going to be the easiest way to do it. So always think, okay, what's the first clean thing I can do before I do something messy? Same concept applies on number 2 over here. We got 2/3 x minus 12 is equal to 6. What's the cleanest thing I can do to get that x alone? Probably not mess with that, right? That guy. So we're going to add 12 to both sides. We have 2/3 x is equal to 18. And for the record, if you guys have any questions or you're getting confused, speak up, mention it in chat, whatever, because I got nobody directly in front of me, so I cannot gauge how confused I am making everyone. So we got that. Well, what are we going to do with the fraction? Same thing we did before, right? We're going to multiply by the reciprocal of that fraction. So same thing upside down. We know those are going to cancel. And we can see that if I put that over 1, the 18 and the 2 can reduce right now. Oh, there's our number 1 right there, is on my finger now. All right. So the 2 goes into itself once, 2 goes into 18 9 times. We have x is equal to, multiply across on top, 9 times 3, 27. And on the bottom, it's a 1 times 1, so we don't have to write that. So 2/3 of something minus 12 equals 6. That something happens to be 27. Sorry, I just got an email about the post-assessment Tuesday. Yes, so those of you who I've told are going to be doing the post-test assessment, which, what did I say? I think it was everybody but Amanda and Kelly. So the other 3 of you. Other 4 of you. Sorry, the participant list got cut off for me. Yeah, all of you do have to be here on Tuesday. And at 6:15, you'll go from this class over to the testing center, which is, right next to Excel, which is right next to this classroom. You've all been here. It's going to be fun. I'll probably forget, but I intend to send you all an email to confirm that. Okay. Number 3, let me write out a few of these real quick. And I intentionally picked some weirder looking problems where the variables in different places, just so you guys can see how to work these out. So even if there's a slight difference in how things are written, the same concepts still apply every time. So for instance, number 3 here, we have 5 minus x over 2 is equal to -3. Okay. First off, our goal is to get x alone. Things that are in the way of it, it's being divided by 2. It's also being subtracted from a 5. The fact that it's being subtracted from the 5, not the 5 being subtracted from it, gives us the problem that there's a minus out front of this x. So we're going to have to deal with that. We're going to have to deal with the 5, the minus, and the 2. We can do the minus at the 2 and the 2 at the same time, but hey, that 5 is really in the way, isn't it? So what are we going to do? Easiest thing to get rid of is the 5. So we're going to move the 5 over. We're going to subtract it from both sides. What do I have left on the left? You have to keep that sign, because when you're subtracting something, that's the same as saying that you have a negative of it. So that negative, that minus, is still on that term. So we have that whole thing left over on here. And on the right, we have -3 minus 5. We're at -3. We're going 5 further down. So it's a -8. Now, how do I get rid of the negative? How do I get rid of the 2? Well, the 2 is easy enough. It's divided by 2, so we know we'd have to multiply both sides by 2, right? We've done that already, but the negative's kind of in the way. Well, I'll show you. We know we're multiplying by a 2. But hey, negative times negative is positive, right? So if I multiplied actually by a -2 on both sides, now I have -2 times negative x over 2. The 2's and the negatives all cancel out. And we just have x. And over here, -8 times a -2. Well, what's 8 times 2? It's 16. And then negative times a negative is a positive. So this ends up being a positive 16. Okay. Any questions? Did I lose any of you on that one? Expecting at least one lost person on that negative sign. That's why I'm putting emphasis on it. That's why I'm giving you so much time to chime in, because if one of you is confused, there's probably a bunch of you confused. I'm not leaning over and grabbing for a drink every time I pause to see if you guys have a question at all. I don't know what you're talking about. Nobody? Okay. Well, this one does the same sort of thing with the negative, right? We're subtracting the term with the x, same as the last one. So we're going to follow the same sort of structure. We're going to subtract 27 from both sides because we're aiming to get that x alone. No, I don't care if it's on the right. The x can be on the right. Some people tell you, hey, the x has to be on the left. No, they're wrong. I don't care what they say. X can be anywhere it needs to be. As long as it's set equal to x, we're good. So 52 minus 27, that's going to be a 25. And that's equal to whatever's left. Remember that minus is still on that 5. We can't lose that. Be very careful. Don't lose signs. That is a sign that gets lost very often. Okay. So at this point, instead of where the last one we had it divided by the 2 and have a negative on it. This one we have it multiplied by 5 and have a negative on it. Okay, well, the opposite of multiplication would be division. So we're going to divide both sides by the -5. On the right, we have an x, because that stuff all cancels, right? On the left, well, 25 divided by 5 is 5. And this is a positive divided by a negative. So it stays negative. Now, right here, I'm done. If it makes you feel better, if you want to rewrite this, oh, -5 equals x, I don't like the look of that. You can write it as x equals -5. You can flip it around if you have to. It does not matter. And in fact, if we can get to inequalities today, I'll show you that sometimes flipping it around is very, very useful. It's really not here, but sometimes it is. Okay. So right now we have 6 over z plus 3 is equal to 6. This one's trickier. You know why this one's trickier? That z is in the bottom. We haven't had one like that at all. So my first thought is, okay, since I know that one's going to be kind of a mess, I'm going to get that term alone like I always do, right? So we're going to subtract 3 from both sides. Okay, so I have 6 over z is equal to 6 minus 3, 3. Okay, now this is where this one gets tricky. So we cannot solve this one right away for z. We cannot, unless you're really good at math, you've done this 100 times and you can see what's going to happen. We can't do that. And yes, you could probably reason your way through this. 6 divided by something is 3. Yeah, we could probably guess what that something's going to be, but you still got to know how to do it. So let's look at our options here. Well, we have something divided by something else. What do we normally do in that case? Well, we usually cancel it out and go with multiplication, right? Is that going to help us? Well, if I multiplied off this bottom over here, that z, all that would happen would be the z would attach to the other side. Oh, but then it wouldn't be in the bottom anymore, right? So that's a good idea. So let's go ahead and do that. Let's multiply both sides by z. Cancel it out. We get 6 is equal to 3z. That looks more normal. That looks like something we can do. So divide both sides by 3, and we get 2 is equal to z. Now, the reason I put this problem on here, because I'm not 100% that you'll see something like this on the exam. It's possible, it's very possible, but I'm not 100% on it. But what I wanted to get through to you guys is that if you get to a point where you don't know what to do, where you have no experience on what to do, think, well, what can I do? Don't always think, what do I know I can do? Just think, what can I do? Sometimes reframing it, just moving that z over, can get us to a point where it's something we actually know how to deal with. So that can be very, very useful. Any questions? So I've glossed over this concept a little bit. We've mentioned it a few times, but we haven't run across when it comes in really useful. So this is going to be where these are useful. So combining like terms. This does not have to be a complicated concept. For some reason, it's taught in a complicated way sometimes. I hate that. Literally, it's like when you tell somebody you're trying to mix apples with oranges, and you know the whole idea behind that saying is that they're two separate things. That's exactly what's happening here. If I have a 5 and I have a 3x, I can't combine those because that 3x literally means it's 3 times some number. That x is some number, right? So if I look at this and I say I have 2x plus 3x plus a 5, I would look at these things and say, okay, so what has like the same configuration? We got 2 things with x's and 1 without. So the things with x's can combine. So you just look at the numbers in front. The numbers in front are actually called the coefficients. So if you ever see that term, that's where that comes in. The 2 in the 2x is its coefficient. Same with the 3 on the 3x, just the number on the front of it. So this 2x and the 3x, since they are like terms, they have the same variables, they can fit together. And that works very well for every level of math from here on. It's just going to be able to keep going. So like, for instance, when I was in like differential equations, I would be combining things that had like x squared y cubed with x y cubed, and I'd have like 10 different ones. And I'd sit there with like a checkbox, making sure that I kept them straight. It can be difficult when you get that far up there, but right now the concept is literally, if they got the same variable, put them together. That's it. Nothing more funky than that. So I also wanted to combine this with evaluating expressions. So I've mentioned expressions and their difference from equations before. All an expression is it's literally an expression of something in math terms. You are expressing something. If you express something, you're just saying something. You're not setting it equal to anything. It's just a thing standing on its own. So evaluating expressions comes up pretty regularly. If you said that your car had, say, 15 miles to the gallon. right? And you were trying to figure out how many gallons you need or something. You could actually just say, oh, well, if I'm getting 15 miles to the gallon, you would say, okay, well, multiply that by how many gallons you got. And that would be how many miles you could go, right? That's pretty basic. That's exactly what evaluating expressions are. They give you an expression, like for instance, this one where it says 2x plus 5, and then they give you a number to plug into it. What is it when x is -5? So you just take that -5, plug it in for the x, and clean it up. So you can see that happening on the bottom row. On the left, you see I just put that -5 in a parentheses. I rewrote my problem, my 2x plus 5, but I put a parentheses where my x was, and I put in whatever I'm substituting. And then you just clean it up. 2 times -5 is -10, and that -10 plus 5 is a -5. Okay. Let me see here. I swear I had, oh, I see what happened. I see what happened. Okay. So we got a bunch of problems. I think we're going to skip a few of them in the interest of time. I really want to cover more ground tonight than we have before. I'm thinking we're going to skip the first two. We'll do 3. We'll do 4. You know what? They're all useful after that. Just 1 and 2 are what I'm skipping. Let me write that down. All right. You knew I'd be making a new problem with fractions at some point, right? It's what I do. I throw fractions in as much as I can. It's not as bad as you think. This one's actually really quick because same thing as always, can't mess with that yet. So we're going to subtract off whatever else there is. Well, so what if it's a fraction? It can go away. Now, depending on the problem, you might have something like this that has a different denominator, and then you'd have to get a common denominator between the two. Right now, we already have a common denominator. They're both over 2. Remember, once you have the common denominator between the two, we can go ahead and combine across on top. What's 13 minus 1? 12. So we have 12 over 2. Okay. Well, that's nice. That's a 6. Now I can divide by 2. Get that x alone. There we go. It's just a 3. Now, yeah, we did have more than one step. How many steps did we just do? 1, 2, 3, and 4. We actually did 4 steps on that one. We subtracted off the fraction. We didn't know quite how it was going to go, so we just rewrote it with the subtraction happening there. So we could combine these two pieces now. All right, cool. Clean that up. Cool. Divide off the 2. Cool. Done. Kind of weird looking, but not so bad, right? And that's actually why I'm not skipping any of the other problems on this page, because they're all kind of weird looking, but they're also nothing harder than what we've done already. So the next one actually has a bunch of decimals. I have 13.8 minus 7.2x is equal to 34.24. Okay. All right. As weird looking as that is, if I didn't have any decimals, this would be a really easy problem, right? So that means it's still a really easy problem. I'm just kind of concerned about the decimals, but we're going to do what we always do. We subtract off the number that we're kind of avoiding with that x, right? That x is what we're aiming to get alone. So we're going to get rid of that. There's step one, subtracting 13.8. Okay. At this point, just grab your calculator. So we have 34.24 minus 13.8. Okay, 20.44. All right. So that's what's over there. What do I have left over here? That thing. Don't lose the sign. You're in a test. You got some scratch paper out to work it. You see that sign, tell yourself out loud, don't lose the sign. If you're around a bunch of people because you're testing, don't say it out loud, but kind of say it to yourself. You know what I mean. You know what I mean. Don't lose that sign. What are we going to do with that sign? We're going to divide it off with that number. I don't care what that number is. Not even a little bit. I see a number multiplied onto the x. All I know is I want to get rid of that number. That's all that is occurring to me at this moment. I got something minus something x is equal to something. What am I going to do? Subtract off that something, cool. Divide off the thing on the x, cool. That's it. So we can take that 20.44, divide it by negative 7.2. Oops, and I'm going to hit enter twice accidentally. And I get that weird looking thing. Negative 2.83889. We're just going to round it to 3 decimals. So negative 2.839. When in doubt, round to 3 decimals. Because this thing actually keeps going on forever. My calculator didn't show me that so much. So I could have put like an 8 and a little bar above it, but honestly, once you get to these types of problems, you're not really going to do that much. You're really just going to go ahead and say, hey, we're going to round to this decimal point and we're going to call it good. Okay. Let's see, what's the next one? Do I have room right there? Yeah, I do. Yeah, I do. Number 5 is going to be 37 equals 3w plus 2w plus 12. It's the first problem we've actually had that has more than one copy of that variable, right? But it's the same variable, right? Oh my God, they're having pizza next door and I'm losing my mind. I just want to say that out loud. It smells like Domino's. Okay. All right, so we have 37 is equal to 3w plus 2w plus 12. What's our problem here? Well, we got 4 terms where we normally have 3, right? Well, since these both have w's on them, they're like terms. 3 of this thing plus 2 of this thing. Well, we don't know what the thing is, but we know we have a total of 5 of it. So we can do that. We're combining like terms. And that's actually one of my personal things is that when I have a more complicated problem, my first step is always combining like terms on either sides of the equal sign. Now, why do I put it that way? Because if I got w's over here and I got a bunch of w's over here, I'm only going to worry about cleaning up each side of the equal sign separately before I start moving things around. That way I have less stuff to move around, right? All I have to move around right now is this plus 12 because I'm trying to get that guy alone. Okay, so subtract off the 12. Okay, Hey, I just got an email saying that a purchase I made that I had to contact their support because it didn't go through properly and they took my money, finally got fixed. Cool. I'm gonna go home and be a nerd tonight. That's a joke because I'm always a nerd. All right. So we got 25 there, we got 5W here. Well, easy. We got the 5 on the W. Divide off the 5. 25 divided by 5 is, guess what? It's a 5. And then we have a W over here, so we're good. Now, one thing I do want to point out, because a lot of people get a little confused when I shift over to a different letter. What's the difference between this X and this W? Nothing. That W is just representing a number that I don't know right now. I do not have a clue what that W is. That makes it no different than an X. We just happen to have written a W. Sometimes when we're making equations, it's very useful to have a letter that represents what we're dealing with. D for distance, R for rate, T for time, etc. Those are just really good examples. Sometimes you'll have this. Maybe it's weight. I don't know. But for our purposes, it's just an unknown. So we're not really stressing about the unknown. Hey, number 6 is a perfect example of what I was talking about a second ago. I have a 2 plus 2x minus 4 plus 9x equals 14 plus 6x. Did I make this intentionally more confusing? Oh, you bet I did. If you feel like I'm torturing you, you can rest easy to know that I am being tortured by the smell of fresh pizza right now. All right. So let's combine like terms. That's really the best thing to do. When you get a problem like this, where you got a bunch of stuff, it's all jumbled, treat each side of the equals as its own deal. That's an expression set equal to an expression. So clean up each expression, clean up each side. What's happening over here? I got 2 things without variables and 2 things with variables. So these 2 can go together and these 2 can go together. So here's the way I like to do these. I like to go from the left and say, okay, this guy. The first thing I'm dealing with is something that doesn't have a variable, right? So I have this one and then the minus 4. What's 2 minus 4? -2. Okay, let's write a -2. Now we've already, personally, this is kind of how I do it. I don't like to cross them out because then I forget what was there or I forget why I'm crossing things out kind of implies that it went away. It didn't go away. We've already dealt with them. So I kind of underline what I've already done. I underline what I've already done, and that way I know I'm taken care of there. Okay, so I got these 2 left, 2x and 9x. Okay, 2 of them plus 9 of them gives you 11 of them. All right, so everything over here is already dealt with. What about over here? Well, I have something without a variable and something with a variable. Those can't go together. They're not like terms. So we call it good. Now here's where we make a decision. Here's where we make a decision. We have on both sides something without and something with a variable on both sides, right? So what we have to do right now is we have to pick a side where our X is going to be. Now, some of you might go for the option of always having it on the left. Some of you might go for the option of always having it positive. I'm personally of the group that tries to make sure that I always have a positive. So I look at my X's and I think, okay, where did -4 go? What's 2 minus 4? -2. Got combined. Yeah. Okay. So what I like to do is I look at my x's and I say, okay, whichever one is the smallest, that's the one I'm going to move over. This is actually, I mentioned earlier that I don't like to skip steps, but sometimes I like to combine them. This is actually where I usually combine steps, because I know that by doing this, I'm going to have my x's over here, right? Which means that the next step, this 2 guy, this -2, is going to have to go to the other side. This is where I like to combine that step. I could add 2 to both sides. That'll cross off over there. Now I got all of my ones without variables. Those are actually called constants usually. We have our constants on one side, and we have our variables on the left. Now I can combine. 11 minus 6, 5. 14 plus 2, 16. Okay, so I have 5x equals 16. Divide off that 5. X is equal to, well, now you got a decision to make. Are we good with fractions? Or are we good with decimals? Personally, I'm perfectly happy with fractions. If you leave it as a fraction, we know it's an exact number, it's correct. And I don't care if it is an improper fraction. We have reached the point in math where we like improper fractions. That's easier to deal with, that's easier to write down. If I am just doing equations, I don't, the whole, hey, how many miles away is this 16/5 doesn't apply, because we're not talking about miles. We're not talking about anything in particular on units. This is a straight math problem. So we get our answer. Now, if that went in evenly or if that reduced, we would of course do it, but since it didn't, we're fine. The next 2 are dealing with evaluating expressions. Why does my 4 look like a 9 where it's missing the top? Okay, so we have 5x plus 4 when x is 7, and we're expected to get a number out of that. So what you're going to do, if this is still confusing you, and actually when these get more confusing, this is actually my preferred method of substituting. We're going to substitute in for that variable. So what I like to do personally is I like to write what I have with a set of parentheses where my variable was, right? 5 times x plus 4. We don't know what x is. 5 times something plus 4. Well, we're given the something. We're given that it's a 7. See how that works? You're just taking that x, you're taking that 7, plug it in for the x, and now all you got to do is clean it up. 5 times 7, 35, plus 4. Well, we can do that real easy. That's 39. Right? Not too bad, not too bad. Okay. Now the last one of these before we hit inequalities. Yeah, I'm gonna write this. I wrote it in a parentheses. I don't necessarily have to keep it in that parentheses, but I am for now. So we have -2/3 x minus 4. Now, one thing to note, this is how I have it written in the slide. Nothing's really acting on that set of parentheses except it's multiplying on the x. So that would be perfectly equivalent to writing it like this. So get used to being able to say, hey, do I need that set of parentheses? What's happening with it? These are the same. Now, I'm going to put a parentheses where my x is, because I know that I'm substituting in. My x is going to be x equals 12. So that's going to be a 12 right there. Okay. Now think of that as being over 1. If that was over 1, I'd be able to reduce it with that 3, right? So I don't necessarily need to put it over 1 to be able to do that. We just know it's going to work out. So that 3 goes into the 12 4 times. Now, how you write it from here, it depends on you. Just for the purposes of being able to see this clearly, I'm going to write this out. Personally, I would have just done the multiplication here. But since you guys are learning, it might take an extra step to be able to say, hey, that's what we have here. And that's fine. Do your multiplication. We end up with -8 minus 4. So we're down at -8. We're going 4 further down. So those numbers are stacking. We end up with a -12. Isn't that funky? Plug in a 12, we get a -12. Not too bad. Any questions on these guys? Okay. So for the next, looks like we have 5 slides of instruction on a couple of different concepts, and then we'll jump straight into graphing lines. So before we do that, what I'm going to do is go ahead and set us up for a break. A little earlier than usual, but it is technically at the halfway point. So we're going to take a break until about 7:25. And then once we come back, we'll be refreshed and excited to do some inequalities, right? Yeah. Okay. So if you need me, I will be sitting here, but I'll go ahead and mute everything. All right, are we happy and refreshed? Those of you who haven't run screaming away, you know. So at this point, we're going to get into inequalities. Inequalities, unlike, you know, what was happening before, well, they're unequal. They're not on a perfect balance, but we still kind of have to treat them like that in the meantime while we're working them out, because essentially an inequality doesn't give you one number as an answer. It gives you a range of numbers as an answer. So something +3 is greater than 2. Well, that could be pretty much anything that gives you the answer where something is greater than 2. Anything greater than 2, it has to be at least 3, right? So, or even 2.01. That would work for being greater than 3. So you kind of end up with a range because even the number 500 would fit for that. 1 billion would fit for that. So you end up with a bunch of different numbers and a nice way of writing them, actually. So you can see from the table, we only have 4 symbols, basically one pair of symbols, and then a variant on them because you could have the bar underneath them. But if they don't have the bar underneath them, if you just have a greater than or less than symbol, The greater than symbol means that the left side is bigger than the right side. Whereas with the less than symbol, it means that the left side is less than the right side. So you kind of read those as left to right. Then if they have little bars underneath them, that means that it could also be equal to that. So for example, if you had to find something that was greater than 2, you might think 3, 4, or 5, but 2 wouldn't work, right? Because 2 isn't bigger than itself. Well, if I had something was greater than or equal to 2, then it could work, right? 2 is also equal to 2. So it essentially goes from having, so if you think about putting things on a number line where you have like the open circles and the closed circles, when it comes to having the equal to option, those would be more of the closed circle types. So it can exist at that point. So with inequalities, they're a lot easier to work out if you end up with the variable on the left side of the inequality sign. I'll actually show you what happens when that doesn't work out. But our operations that we normally do for, say, all of the equations we were doing before, we do the same things. We just leave that weird little symbol in between alone. So we kind of treat it like the equal sign before. The only time you end up changing that is this sentence right here. If you multiply or divide by a term with a negative sign attached, that switches which side is bigger than the other. Because of this, anytime this type of operation takes place, you have to change the direction of the sign. So a greater than would turn into a less than, or vice versa. Because I mean, think about it. If you have like -5 is less than 6, and suddenly you switch the negative to the other sides, and you add 5 and -6, it wouldn't make a whole lot of sense to say that 5 was smaller than a -6, right? That's what ends up happening, is it actually changes which side is bigger. Now that makes a little bit more sense when we look at interval notation. Interval notation is a nice way of writing problems. Helps when I copy these over and it doesn't like completely jumble up how things are in here. That'll work. So interval notation is actually a way of writing subsets of the real number line. So a closed interval is one that includes its endpoints. For example, this set, now you're not going to have to remember writing things this way. That's called set notation. Don't worry about it right now. When you would see that would be like a statistics course. We're not a statistics course. I want to give you easier things to do. What we're going to be doing is a lot easier. So interval notation is actually written with brackets and parentheses. If you have, let's say, greater than or equal signs or less than or equal signs, so these guys, because it can include those endpoints, if you were drawing it on a number line, see you have those closed dots on the end. Those closed dots mean that it can include that point. So when you work with interval notation, those closed dots are represented by brackets. So if it includes the endpoints, you use a bracket. Now, if it doesn't include the endpoint, if you have an open circle, you would use a set of parentheses. That's an example of this guy. The last one was a closed interval. This is called an open interval. Not going to be stressing those terms very much. All we're really going to be looking for here is being able to recognize when you'll use a parentheses, when you'll use a bracket. Now you'll also notice that they're left to right. You literally look at what you have on the number line and you say, okay, -3 doesn't include that -3. We have an open circle, which means over here, you're going to have a parentheses and then the -3. You put a comma and then you go to the right side of that interval. You look at your number line graph. Okay, it goes all the way up to 1. It doesn't include that 1. So you put the 1 back over here. And since it doesn't include that 1, you put a parentheses. This right here, this interval notation, it looks like a point on a graph, but it's actually interval notation in this case, is telling you that we have an interval from -3 to 1. And since it's parentheses on both sides, it doesn't include either one of those endpoints, but it's all the space in between. Whereas, let's go back to the last one. It was the same thing, same numbers here, but in this case, it had brackets. It had brackets because it included those endpoints. On the negative side of things, we went from -3 to 1 the same way, but it included the -3, so we have a bracket. Then it goes over to 1 and it stops, and it included 1, so it has a bracket. You can also, and don't be intimidated by the last one, that's not as scary as it looks. You can also have intervals that are half open and half closed. So if you look at that, just the number line, don't stress the numbers on the screen right now, but just look at the number line. It goes from -2 to 4, right? On the left side, the -2, well, it's included right there. It has a closed circle. On the right side, over there at the 4, it's not included, it has an open circle. So it went from -2 to 4. It's included on the left, and it's not included on the right. Now, this next one I put on here because I'm not 100% if you're going to get weird things on the HiSET. You know, I haven't actually taken the HiSET exam myself. I've just looked at a lot of books about it. So I've only seen 1 or 2 examples that look kind of like that last one. I wouldn't stress it too much, but all you got to do is look at the number line for that last one. Just look at the image. On that image, we have, 2 separate intervals and then a dot, right? On that first interval, we have -4 to -2, and it's included both sides. So it would look like this guy over here, right? Now, the one in the middle is the weird one. The one in the middle is the weird one because it goes from -1 to 2, but it actually has a hole in it at 1. So you actually treat that as 2 separate intervals. It goes from -1 to 1 because it doesn't include 1, it stops there, right? And then you have another interval, 1 to 2. So you have the -1 to 1, you have a 1 to 2, and it's including on the 2, so that one's a bracket. And you see that dot on the 4, you don't see that very often. It's just kind of represented by the little curly braces, and it's like, yeah, there's a 4. And in order to join all of those intervals together, you do this little U thing. That's called union. I don't think we have any problems on union. Don't stress that screen so much, but it's good to have kind of like, it's good to have at least a visual on that sort of thing before we get any further. Hey, look, we have inequalities. So I kind of covered all of our bases with these 4 examples. If I remember correctly, they're kind of all, let me see here. I want to change some signs around here. because I did this last semester and I ended up having all of these facing the same direction. And I don't want it that way. Okay, so now it's actually going to work out. So every one of these, I have it set up so we're going to solve the inequality, then we're going to graph it on a number line, then we're going to show it in interval notation. And once we do it on the number line, most of you are probably going to have one of those oh moments when it comes to the interval notation, because it looks complicated. It's not even a little bit. I am hearing loud music from elsewhere on the campus. I feel like I'm living in the California Valley again. All of my neighbors blasting their music constantly. I just kind of accepted it. It was the background to my Spider-Man cartoons, because you know, I'm that nerd. You could probably make a blind assumption about me, and it would probably be true. I am the reason there are stereotypes about nerds. Okay, so, oh my God, we have a problem. Oh my God, look how much space I gave myself. I wrote on all the problems. This isn't going to be bad. Don't freak out. So we have 3x is less than a 9 plus 3. So what you're going to do with these problems is you're going to solve them just like any of the equations we've done before. And the only thing we got to do, we got to watch to make sure that we keep that sign going in the right direction, unless we multiply or divide both sides by a negative number, then it flips. Otherwise, we're going to treat it like an equal sign. We're just going to solve to get the x alone. So we have 3x is less than 9 plus 3, so that's 12. Well, I can solve for that x by dividing off the 3. And we get x is less than 4. Cool. Just like any of our other problems, right? Not too bad. Now, on a number line, you're going to see how truly lazy I am when it comes to graphing tonight. There's a 4. Let's do some numbers around it. There we go. That's an awful looking number line, but it's a number line. That's how much I care about these. That's it. That's all we're really worried about, is that we got the 4 and we got some room around it for it to move. X is less than 4. What does that mean? It means that our x is everything less than that 4. So we're going to fill that in. Over here, we're even going to have the arrow going to the left, because literally everything less than 4 is our answer. Negative 5 billion? Yup, it's on there. Negative 20 trillion? Yup, it's on there. My bank account? Totally in there somewhere too. Not happy about that one. X is less than 4. Look at that sign, less than. If it's less than, or if it's greater than, it doesn't include the endpoint. So it can't be 4, it has to be smaller than that 4. So open circle right there at the 4. Uh-oh, now we got to interval notation time. Now, one extra thing that I did not put on the slides is what happens if it goes on forever. What happens if it goes on forever? How do we say that? And what that is that's actually going to be an infinity symbol, kind of like a sideways 8 that goes on forever. Now it sounds a little weird, but for the use of our number lines, if it went off forever here, that'd be infinity. If it goes off forever in this direction, well, that's going down, right? So that's going to go to negative infinity. Now, can I ever include the last number in infinity? No, that doesn't make any sense. So anytime you have interval notation that deals with an infinity symbol, it is not going to include the endpoints. In fact, this one doesn't include any endpoints, right? Because this is an open circle. So when we do our interval notation, we think, okay, furthest left, well, it goes on forever. We don't have a furthest left. So you write negative infinity. We have a comma, and we go to the furthest right, that 4. Okay. Do I include the last number in negative infinity? No. So we use a parentheses. Do I include the 4? No. It was an open circle. It didn't include the 4. So we use a parentheses. There we go. That's our interval notation. It's literally just a transcription of a number line. That's all it is. Probably didn't cement in your head quite yet, so let's look at number 2. Number 2, we're going to divide both sides by 2 to get that y alone. Now, one thing I want to say, this is a negative being divided. Does that change the direction of the sign? No. It's only when we are dividing or multiplying by a negative number. This number that we're transferring around has to be the one that's negative for that sign to change. Otherwise, it stays the same. Draw some points around there. There we go. There's some points. All right, it's a number line, I promise. So where I usually start, I know I had it a little different over here, but where I usually start is I look at this and I say, okay, we're at -4. We're not including, so it's an open symbol right here. Now, are we going above it or below it? Y is greater than -4. That means it's bigger than -4, so we're going above. Okay. All right, that's it. That's graphing our inequality on the number line. So what are we going to do? Well, let's set up our endpoints for interval notation. Doesn't include either side. Okay. So we got a parentheses on both sides. On the left, we have a -4, comma, all the way on the right. Well, that keeps going forever. So we're going to have an infinity symbol right there. Okay. All interval notation is a transcription of that number line. That's it. Not too bad. Okay. I just got to ask, can you guys hear the music from the next class over? Can any of you hear it? I'm just curious at this point. Okay. So, number 3, we got 12 is greater than or equal to x plus 5. Oh, you can't hear it? Okay. Well, we got, well, it's you know, an English learning class. So we got like mariachi music, like jamming over there. So that's why I'm like, yeah, this reminds me of living in California. So that was all of my neighbors. That said, I think there's only like 2 or 3 taco trucks operating in Carson City, and I'm offended by that number. There needs to be like 30 or 40, like constantly. Like as it is, if I want something good, I gotta go all the way to the Lady Tamales, and that sucks on a bicycle. All right. And yes, I'm totally plugging the Tamale Lady. Totally plugging Tamale Lady. During the entire pandemic, I was like, oh my God, we got to keep her in business. I got to keep throwing money at her. If that place goes under, I would cry. All right. So I'm going to Yeah, all right. Yeah, I'm doing math. That's right. I'm hungry. I haven't actually eaten today. I'm very hungry. And now I have tamales in my head. Yeah, okay. Cool. Math. I'm awake. Hey, guess what? This is easy. Subtract 5. We get 7 is greater than or equal to X. Now this, I put this example on here because I expect people to make mistakes when they do this type of problem. This is 100% a problem that I have seen upwards of 50% of people make. I am not even kidding. This is something where people make mistakes on it constantly. So first of all, we're at 7. It's greater than or equal to. So we know that it's a closed circle. Anytime it can be equal to that point, it's a closed circle. Okay. Which direction does this go? You might look at this greater than and say, oh, it goes this way. But you would be incorrect, because what this is saying is it's saying that 7 is greater than X. It's saying 7 is bigger than anything in X. That is confusing to wrap your head around. I hate thinking about this, right? So this is why I put in the slideshow that it's better to have these ones where the X is on the left. It didn't matter before when we were doing the equations, but for the purposes of the directions, it's very useful to have the X on the left. So what I'm going to do is if I swap the left and right sides, that is going to change the direction of the sign, right? Because if 7 is bigger than X, then that would mean that 7 is still bigger than X over here, right? Now I can read this as X being less than or equal to 7. Reading it that way makes this much more easier to understand. We can now see that it's going to go this way, whereas it's kind of hard to understand that up here. So if you end up on an inequality and you have the X on your right side, after you've solved it, just flip that guy around and then you can graph. Now this one goes on to negative infinity, right? We can't include the last number in negative infinity, so it's going to be a parentheses, comma, our right endpoint, 7. Do we include that 7? Yes, we had or equal to's. So you would use a bracket for that side because we include that side. Okay. Everybody with me, or are you horribly confused? Feel like it's 50-50. I'm getting no feedback, but I'm getting like a, I don't know. I just feel like I'm confusing everyone. So whatever, let's keep going. Let's do another. So this one, obviously it can combine on the right side of negative y is greater than or equal to 5. At this point, I have a negative y. I don't want a negative y. I want a positive y. I just want y is equal to, or unequals in this case. So I'm going to have to get rid of that negative. Now, if you just have a negative on something, no weird number, not negative 2y, not negative 6/3 y or something funky. We just have a negative. What you're going to do is divide both sides by a -1. That's going to take care of that negative for us, because a negative divided by a negative is a positive, and anything over 1 is itself. So we can get away with dividing both sides by a -1. 5 divided by a -1 is a -5. Now we've divided by a negative number. That's exactly what I was telling you guys to watch out for. We want to watch out for dividing or multiplying by a negative number. right? So I divided by -1, which means this changes. This is no longer going to be a greater than or equal to, it's going to be a less than or equal to. From there, we can graph this exactly like this one. I changed a couple of signs and I still ended up with 3 out of 4 facing the same direction. Whatever. So we're at the -5. We're including it. So we have a closed dot. And it's everything less than that -5. So it's everything over here. Okay. So again, interval notation, we're all the way out here at -infinity. So we have a parentheses around that part, comma, then we go to the right side, that's included, and it's a -5. Okay. And that is all I have for these essentially one-dimensional inequalities. Do we have any questions on these guys so far? Are we feeling okay? Let's move on. Fun stuff. Lines in the coordinate plane. So this is, I'm kind of sad that we're only going to have enough time for about half an hour of this class. So, you know, we're going to get as far as we can. I'll explain the concepts behind everything, and then we'll do some problems. So essentially what we have here is a coordinate plane. It's also called a Cartesian plane. So it's made up of 2 lines that cross each other at 90-degree angles, you know, so everything's kind of squared off. Where they cross each other in the middle at the 0 is considered the origin. So that's the very center. And the vertical line there is considered the y. The horizontal one, the one going left to right, that one is the x. So we have an x-axis, we have the y-axis, and as the x is moving to the right, that's where it becomes positive, kind of like the number line. You know, everything to the left is negative, everything to the right is positive. And then with the y-axis, the vertical one, you can think, okay, everything up is positive, everything down is negative. Same sort of thing. Now the center point, these all have essentially coordinates. Let me see if I can, yeah, this one works out nicely. So let's look at a point on this graph. This point, it's kind of written like interval notation, but it's not. Every time you have a point, it's given in the format x comma y in a set of parentheses. That is a point in space. And that's essentially how far away it is from the origin. The first one is always x, the second one is always y. So the point 3, 4, let me see if I can figure out this this annotation thing. I don't feel like you guys can see where I'm pointing. There we go. Can you guys see that red dot? I think that kind of works. Whee! Okay. Going to blindly assume you do. Okay. Awesome. Thank you. So essentially, you look at this point, 3, 4, and you think, okay, that's where this thing is. It gives you the x coordinate first and then the y coordinate. So you start off at the origin and you move horizontally for the X value. So the X value is 3. So you go 1, 2, 3. And then you worry about the Y value. The Y value is 4. So you go up 4. 1, 2, 3, 4. You put a dot there. And then you have the 3, 4. You kind of label that right next to it. Sometimes labeling is useful. Sometimes it's not. For our purposes tonight, it's going to be very useful because we're still going to be learning the planes. And another thing that's useful is you can actually write an X on the X-axis and a Y on the Y-axis. I didn't always do that because these are actually now how do I make it go away? These are actually all screenshots from the Desmos website, which is a graphing calculator website. So yeah, some of it worked out and some of it didn't. So when it comes to graphing, we do a dot. And then if we have, say, a bunch of dots, we can make a line. Now, before we look at how to graph on a line, let's look at an example here. Gonna kind of, there we go. So this line here is in standard form. Standard form is AX plus BY equals C. So something X plus something Y equals something. So standard form basically has all your variables on one side and some constant number on the right. We're not going to think about that too often. When standard form actually comes in really handy, you're going to forget that it's called standard form. So we're not going to worry about this too much. So that is a set, that is an equation of a line, 3x plus 2y equals 4. And every single point along that line is an XY value, kind of like the point that we just graphed, right? And every single point actually works as a solution to 3x plus 2y equals 4. So because of that, what we can actually do is we can make up random points. We can take points, plug them into, say, X, solve for the Y, and we would have a point that we could put on a graph. If we get a bunch of them, we can draw a line between them. And that's the concept that we're going to be exploring in the next few slides. And that's graphing by plotting points. So this example is actually in a form that is useful. It's actually called Slope Intercept form. I don't know if we're going to get that far. We might, we're probably not. I doubt we're going to get that far, but this is probably the most useful form of a line that I know of. And it's really easy to plug things in. So for example, we have y equals 2x plus 1. This is the most basic example of a just a line to graph. Oh. It's the name on my YouTube channel. I'll actually put that in the wide chat here. Actually, I'm logged in. Oh my God, how do I get rid of that? There's the name. All of these views are me. Oh my God, I accidentally clicked on me. That's a horrible thing. All of these views are me. None of you are using this. I actually, unless there's a huge ask for it, I'm probably not going to be uploading classes for future classes that I make, because this has not been utilized at all. But you can even see that there was the entire previous class that I taught. So you guys totally could have like looked at the playlists and jumped ahead, because hey, look, here's the last class that I managed to do last semester. Guess what we were doing? Oh, we actually did hit the slope and intercept that time. Okay, whatever. So we're only a little bit behind the other class. That's fine. That's fine. So let's get back to this example. This example is actually really easy, because usually when you start learning these, they'll give you a table. And the table gives you either values in X or Y, and then you'll have it blank on one side of the table. What you do is you take whatever's in the X, you substitute it over here, you know, kind of like when we were substituting things into expressions, and oh my God, it all builds onto itself. And then you figure out what that gives you for Y. You figure that out, you punch it in over here. So you can easily find sets of points along that line and graph them that way. So I pick these numbers, and I usually pick very similar numbers every time I do graphing by one of these. I like to pick them very close to the origin, very close to the zero, because I like to keep my graphs nice and neat and small. You could plug in X equals 500 if you want to. You're just going to be there all day and grabbing extra paper to staple on to where you are. You know, try to keep them nice and neat. So it's going to make not only the work you have to do nice and easy, but also the graph you have to draw nice and easy. So here's an example of plugging in X equals -2. So you work it exactly the same way that we were plugging things in earlier today. So you work them out, you get something neat, you plug it into the table. You might have to do it 3 times. In fact, it's recommended to do 3 times. Do 3 points anytime you're doing a graph like this. Technically, you can do it at 2, but the reason that you don't is that 3rd point is effectively a check. You are making sure that you didn't make a mistake, because if you do 3 points and they're not all along the same line, you know you made a mistake somewhere. So what you would do is you would plug those points in onto your graph. Let me get that annotate spotlight out here again. There we go. So we have the point -2, -3. So you start at the origin. We work on the X first. 1, 2 back on the X for -2, and then 3 down on the Y. And there we go. We have -2, -3. Then we have the point 0, 1. So if the X value is 0, it's not going anywhere left and right. It's just going to go, it's going to stay on the axis. And then the Y value is 1, so you move up to 1. So that's our 0, 1. Now we have the point 2, 5. So X2, Y 5. So start from the origin. X goes over 2. Y goes up 5. And there you go. And if you see that these are all nice and neat along a straight line, you can draw a line between them. Normally, since this is a screenshot, it didn't work out too nicely, but normally you want to make sure you put arrows on the end of these lines, because it's not just where you drew it, it is everywhere. It goes on forever in both of them. You're confused how I got the Y numbers? Okay, well, let's go back. This is where we got the Ys. So when you have those X's, you're going to take those X's And for each one, you're going to substitute that x into the equation. So for example, this is just an example of x being -2. So you plug in the -2, you get -4 plus 1. So it turns into a -3. So you take that y equals -3, you plug it in over here. You would do the same thing for the others. Say if x was 0. If x was 0 right here, we'd have 2 times nothing. Cool, that poofs, that's not a thing. Plus 1. So I have nothing plus 1 is 1. And then if I plugged in a 2, 2 times 2 would be 4, plus 1 would be 5. So it's all about taking those x values and plugging them into the equation of your line. This perfectly encapsulates how my brain works. All right. You ever just say something stupid and you're just like, I'm going to think about this at 2 in the morning for the rest of my life? I'm definitely that kind of person. Okay. We're at our first graph. God, I really want to get to slope. I think we'll do 2 of these and then we'll move on to the next concept. And that will probably be as far as I can really take it tonight. If I can make it that far. So y equals 3x minus 2. We're going to make a graph out of this guy. We're also going to make a joke of why I ended up picking out a dot matrix graph, because I never actually pay attention to the dots and I just make a giant horrible mess. So we have 3x minus 2. What we normally need is a table of values. Now, since we're not given one, we're going to make one up. Now, usually I pick something on the negatives, something on the at the origin, and then something in the positives. The reason I do that is so I kind of have like a well-balanced graph. I don't have everything on one side or everything on the other side, and it's all really close to the center. So it makes my life easier. So I'm going to kind of do this in a weird looking way so you guys can see how we're working these. I'm going to do them kind of quick because we only have so much time, but it's going to be exactly like the problems we did earlier. Okay. So we have y is equal to 3x minus 2 on every one of these. So it's 3 times something minus 2. Remember, I do the parentheses for substitution. Plug in that -1. Let's bring that down a little bit. So plug in that -1. We'll end up with -3 minus 2, which is a -5. So for that x value on our table, we now have a corresponding y value. Plug it in. Okay. We do the same thing over here. Y equals 3 times something minus 2. Okay. That something is 0. Okay. Well, what's 3 times nothing? Nothing. So I don't even need to write that. The only thing left here is that -2, which is great. Here's a hint. It's always just that if you plug in 0 for x. See that? There it is right there. That's what I really want to get to. That's called the y-intercept. It's what I really want to get to tonight, but I'm probably not going to be able to. I might just go ahead and do a little mini lesson before we get to the practice exam on Tuesday, just so I can at least introduce you guys to slope and intercept. So in this case, it's a 1. Y is equal to 3 minus 2. So y is equal to 1. Okay, there we go. So we have our 3 points that we're going to be graphing on this thing. I'm going to show you how to make a graph really cheaply. This is horrible. You're probably going to give math teachers in the future like an aneurysm. I don't care, sucks to be them. I only worry about my range of numbers that I have over here. My X is my horizontal axis. You know, I got my Y axis happening. I'm just going to kind of do like a light tracing. I don't know how far I'm going to go quite yet. But for the X values, I'm only really going to -1 and 1, right? I'm not going to go any further than that on my graph. With my Y values, I'm going from, my range is between 1 and -5, right? So I'm not going to worry about going higher than 1. You know, I mean, this thing's big enough to put to 2, but you know, whatever. I'm really worried about making sure it goes all the way down to that -5. Now, if it makes you more comfortable, you can label these as you go. I usually only do a couple here and there. But if you're still learning and you're still a little confused, that's fine. You can go ahead and do that. You can go ahead and label these however you want to do that. So we got the negatives here, we got the negatives here, positives here, positives here. Okay. All right. Our first point, -1, -5. X, -1, Y, -5. So you start from the origin. X, we're going to go -1, so 1 back. Y, -5, so we're going to go 5 down. Draw our dot. I like to label these, especially when you're learning. Kind of do it tiny. Might not even see that on the camera. I don't know. But just so you can go back and look at it. And sometimes you can see, hey, if I made a mistake, I can eyeball it and say, oh, God, that's why I made a mistake. Sometimes I'll see people put this at -5, -1, it'll be like over here or something. So that's just a good thing to do when you're learning these. Okay, when X is 0, it's not going left or right anywhere. It's staying on the axis. Y is -2, so we're just going to go down 2. So that's the point 0, -2. And then we have the point 1, 1. That one's awesome. We're going 1 in the X and 1 in the Y right there. 1, 1. Are these along a straight line? Yes. So we go ahead and draw a line between them, put our arrows on both sides, and we're good. That's it. That did not take long. That took us, what, like 5 minutes? It looks like a lot of work. It's really not. It's just about keeping things straight. So let's review that real quick. We had some X values. We were filling in our Y values. So for each of our X values, we plug them into our original equation. So we plug that in here. We got a Y, we put it in our table. We plugged in 0, we got a Y, we put it in our table. We plugged in 1, got a 1, put it in our table. We treated each of these as separate points. We put them along our graph, going from the X value first, then the Y value, X value first, Y value, X value first, Y value. And if they're along the same line, we draw a line between them. Put arrows on both ends, and we are good. That is how we draw a line when it comes to plotting points. Let's see about another one of these guys. Liking number 3 is going to be the last one of these ones I do tonight, because I want to at least show you the other stuff. I don't know if I'll have time to work it out for an exercise. So if you have time, go on essentialed.com and do a lesson on it. They're only, the lesson video is like a couple minutes long. Then you have a couple of questions on it. It's really easy, helps out a lot, and it really ingrains the stuff in your brain. So the reason I picked this problem is because it's not set up like the other one. And I'm going to tell you guys right now that honestly, when you're learning this stuff, it's going to be easier if you have a y equals. So I'm going to show you how to manipulate this thing to have just the y equals. So think about it like any of our equations. If any of our equations we were trying to solve for that y, how would we do it? Well, we'd get rid of this thing, and then we'd end up dividing by 2, right? Well, I don't care that this has a variable. I can still subtract it from both sides. I'm going to rewrite it. 2y is equal to. Now, over here, even though I'm subtracting this, it's generally better practice to have the thing with the x go first. So we're going to have minus 4x plus 8. Okay. Now we have the 2. We're going to divide everything by 2. Unlike our other problems when, I told you we couldn't really do that because it divides everything by 2. This is when you have to do it. If you have multiple things on one side and you're dividing that side by 2, you have to divide everything on that side by 2. You have to. Now, this one works out great because, let's face it, I intended it to. Now, for the purposes of us saving on time, I'm going to go ahead and work out these values quickly. So let's pick, doesn't really matter, but let's go a little further out. Let's do -2, 0, and 2. Now, in the interest of time, like I said, I'm going to kind of eyeball it. You can follow along with me. -2, if I plug that in for x, I would have -2 times a -2. That's a positive 4, right? So 4 plus 4, 8. See, I plugged in 0. If x is 0, this whole thing goes away, right? -2 times nothing is nothing. So I would just have that plus 4 left, 4. And then if I plugged in a 2, I plug in a 2 here, -2 times 2 is a -4. -4 plus a positive 4, well, that kind of cancels out, right? We end up with a 0. So we go ahead and graph this. Our y kind of goes up kind of high, so I'm going to kind of like that. So our x's go from -2 to +2, right? Our y's go from 0. I'm going to kind of put some marks down here, even though I don't really need them, just so it kind of looks like a proper graph. 0 to 8. We want to make sure these are as evenly spaced as we can set them up. So there's a 4, 5, 6, 7, 8. Oh my God, I worked that out just nicely. I don't know how I thought I was going to have to draw the line out a little further. Whatever. And then we're going to put the points on them. We have x is -2 when y is 8. So we start from the origin. X is -2. Y is 8. Right? That's a y. -2, 8. Okay. Okay. Now we have the point 0, 4. So that's on the axis. X isn't going anywhere, right? It's just going up to 4. So we have the point 0, 4. And then we have the point x2, y 0. So when x is 2, y, it doesn't go anywhere. So that one's actually hanging out on the x-axis when that happens, because we have nothing in terms of height. We're along the same line, so we draw a line between them. Put arrows on the ends, and we are good. That is how we graph a line. So these aren't too bad, right? Like this part's a little screwy, but this is honestly just to make your lives a little easier. It's gonna make your lives a lot easier if you solve it for the y first. And I'll actually show you guys why right now. Now, don't forget, I will scan in these notes later. So if you didn't scribble quick enough, you can always take a look at the notes. I'm gonna scan them right after class. They're gonna be on the Google Drive folder by 9. So yeah, equations of lines. This is what I really wanted to get to. I know we only got 7 minutes. We're not gonna be able to do a whole lot with it, but this is what I really wanted to get to. And this actually pertains directly to the lines we just did, because the form that I said I like, the y equals something x and then plus something, ends up working out perfectly with these concepts. Now, before we move on, this is essentially leading into a different way of graphing lines where you don't have to draw out a table. You don't have to plug something in every time. You can just eyeball it, but you have to understand what the slope is first. So the slope, I mean, think about it. It's a slope. It's how something is kind of like what its angle is, right? It's how tall something is. You think of the slopes for like skiing, you know, you have steep ones, you have shallow ones, that sort of thing. That's what this is doing. The slope is found using any 2 points from a line and plugging them into this equation. Now, this equation looks complicated, but I promise you it is not, because think of this as 2 points. All this is right here, x2 and y2, that's 1 point. That's some point that has an x and some point that has a y. And it's subtracting a different point that has an x and a y. So all it's doing is you're getting the change, you're getting the difference in height, and you're dividing by the difference in width. And that actually gives you the slope between any 2 points. So that's what I have explained right here, that you're just picking these points and you're saying, okay, well, we have 2 x's and 2 y's. So how are we going to call these things? Okay, we're going to call one of them x1, y1 because it's our point number 1, and x2, y2 because it's our point number 2. So you're literally just throwing numbers on them and saying, yeah, that's 1 point and that's the other point. So here is where that goes. I know that's terrifying looking, but really, this is step 1, as that's the formula. This is you plugging it in. This is you cleaning it up. And then you just clean it up as far as you can go. That's it. Once you get to this point, you're almost done. And that's literally step 1. So for example, this was our example problem, right? The y equals 2x plus 1. And these were 2 of the points that were on that. So it doesn't matter what points you pick along a line, as long as they're on your line. So you designate them 0.1 or 0.2, and then you plug them in. Look at that 2, 5 right there. X is 2, y is 5. Well, there's our y, there's our x, right? So you're plugging in x and y, and then you do the same thing with this one over here. We have another point. This one's x is -2 and its y is -3. So you do this y minus that y, and that's the top. And then on the bottom, you have this x minus that x on the bottom. That's it. It's literally just subtracting the x's and subtracting the y's between 2 points. So in this particular case, since we were subtracting negatives, you have to change it to a positive. You add them together and you get a number. Now, this is where that is all ending up. This is the slope intercept form of a line. Based on that formula, you can find the slope on any line. If you have a point on any line, the points are in X and Y, right? So you could take that X and Y, you could take a slope, you plug them in and you figure out what this guy is. This guy is the y-intercept. Let's go back to our notes. Let's go back to these. Look at this guy. This is in our formula, y equals mx plus b. This is telling us our slope is 3 and our y-intercept is -2. Let's look at our graph. What did we get? Oh, our y-intercept was -2. What's our slope? Here's the nice thing about slope. Slope is rise over run. I want you guys to understand this for when we are doing more complicated problems. This is incredibly important. This is the change in y, so the change in height over the change in width. Look at our slope here. This is in y equals mx plus b form. In this case, our m is 3 and our b is -2. Okay, think of that m as being 3 over 1. From any point on this graph, you can go up 3 over 1. You can go down 3 and back 1. If you find one point on any of these types of problems, you're pretty much done. Because all you have to do is move in terms of the slope and intercept. I know I'm cutting it on time. I just want to show you guys one problem. Y equals 2x minus 3. Just to have it in your head before you do an assessment, before we get to the weird practice test stuff next week. This is how easy slope intercept form is. Please, over the weekend, do anything on Essential Ed that has that. First, this is your y-intercept. You start at -3, you draw a dot. Your slope is 2 over 1, basically. So you can go up 2 and over 1. As many times as you want. Up 2 over 1, up 2 over 1. You can even go down 2 and back 1 if you want to. Look how quickly I just did five points on this line. That's graphing with slope and intercept. I know my line is crooked, I don't care. But that's graphing with slope and intercept. That is literally it. You find the y-intercept, draw a point there, and then you take your slope, and your slope is always rise over run. So you're going up that, over that. Why am I cramming this? Well, because next week's the last week. Several of you have a post-assessment on Tuesday. I really want you guys to do okay. So that, other than all the stuff we're going to cover on the next, on the practice stuff, when I go over that, that is the last of my direct lessons. So I hope that works out nicely for you guys. I'm sorry I had to rush this. This is useful. Please remember it. And by please remember it, I mean, honestly, please look it up at some point. You're not going to remember this. But yeah, that's it. That's all I got. You guys are done. I'll see you Tuesday and we will start practice testing. It's going to be fun. Yeah, no? Everybody scared? Everybody left? Cool. Have a good night, guys.
Thank you, and have a good night.